Welcome back to Masters for Operations 2. In this lecture, we will be discussing on the manufacturing of membranes, advantages of membrane separation processes, limitations and approaches to improve the membrane performance. So, we will be discussing first the manufacturing of polymeric membranes. So, there are 6 manufacturing processes for the polymeric membrane fabrication. That one is this phase inversion technique, then another is template leaching, and one process is electro spinning, and another process is sintering, and one process is track etching, and another process is stretching. Okay. So, out of this we can say we will be discussing mostly this phase inversion techniques and electroplating processes, because these are very, we can say, this widely used and new manufacturing processes, whereas we can say this on template leaching, sintering, stretching and track etching, these are all well established studies. These polymeric membranes like this, if we talk about this phase inversion techniques, then we can say the pore diameter will range from, we can say, less than 0.1 micron to greater than 20 micron. So, in the wide range we will be able to manufacture the membrane using this phase inversion techniques, and we are able to prepare these both porous and non porous membranes, means with porosity, high porosity as well as low porosity. And the properties are like this, we can say these properties varied according to polymer used and easy and widely applicable. In case of the electrospinning, this is, we can say, it is a highly porous, we will be discussing this one. It is done by electrowinning, and porosity may be sometimes like this more than 80% also, and flux value is very high and less tendency to fouling and high surface area. In case of the sintering, we can say we will be able to get the pore diameter from 0.1 to 10 micron. Here also we can say this on in a wide range of membrane pores are this one manufactured using the sintering process, and porosity varies from 10 to 20%. So, we can say this one, it has outstanding chemical, thermal and mechanical stability, and organic and inorganic materials can be used actually for the separation. And stretching, this one using the stretching also we are able to make the pore diameter from 1 to 20 micron, and porosity is also here very high, to 90% porosity is observed, and high permeability for gases and vapors can be produced as the flat sheets and tubes. And for track etching, we can say the pore diameter ranges from 0.02 to 10 micron like this, and maximum 10% porosity is observed. It has this low tendency to plug and good long term flux stability is observed. And for template etching, we can say this one minimum pore is observed like 0.05 micron, and it is highly porous and high surface area is available using this template leaching. Okay. So, in phase inversion techniques, we can say this, it involves the precipitation of polymer from the polymer rich casting solution induced by solvent and non solvent miscibility. So, the polymer creates the membrane structure and the non solvent makes the pores. Suppose we have this polymer solution, it is dissolved in on suppose organic solvent, and then say whenever it is mixed properly, say for a long period of time, then it is now placed in the say glass plate, and then using this digital film applicator or casting knife, so we are able to make a film using this polymeric solution. Then say we need to put inside this, then we can see inside this film the polymer as well as this organic solvent is there. Now, we are using one coagulation bath, so where we use water, or we say cold water as the phase inversion medium. So, whenever it will be coming, then polymer from the liquid will be converting into the solid phase. So, that phase will be inverted here, and then say we can say this phase inverted membrane actually will go for this, we can say the rinsing and as well as this post treatment, means then so drying is done in different temperature zones. And in case of this electrospinning process, say a fiber spinning technique depending on the electrostatic force of attraction is used for the preparation of electrospun nanofibers membrane. An electric field is created between the, suppose this we have this one feed here, and using this syringe or we can say the injection pump, suppose this membrane nanofiber, say fiber, this membrane actually is now injected, and suppose this needle of this this syringe is made positively charged, this one what is called pole, and there is one rotating disc collector, suppose it is rotating in a, say maybe in cyclic, we can say this one in the clockwise direction or anti-clockwise direction, and then needle actually will be moving from the, say one side of this rotating disc collector to the other side of the rotating disc collector, and at the same time rotating disc collector will be rotating in the, say we can say this one either we can say this one clockwise direction or anti-clockwise direction. So, in this case there are two different types of movements. One movement is from, suppose one side of this rotating disc collector to the other side, that is we can say this one movement of the needle of the syringe. Another movement is this, which we can cyclic rotation either clockwise or anti-clockwise, that is the direction of rotation of the rotating disc collector. Okay, and then, so due to this winding, actually we can say this one, the membrane film actually will be produced. So, produced fiber in the nanometer to micrometer range will be there. It is depending on so many parameters, and the polymer chain entanglement, so within the solution prevents the electrospinning jet from the breaking up. And then whenever say we have so many rounds of the rotating disc, and say from the needle of the syringe, the we can say the jet is coming out, and this, suppose the rotating disc is negatively charged. So, due to this charge distribution, whenever the polymeric this one fiber will be coming out, it will wound actually on the rotating disc collector, and ultimately it will be obtained as the film. And so, we have some, we can say functionalization of the membrane for specific applications, like this membrane modification can be done using different techniques, such as we can say this polymeric coating or blending, graft polymerization, then plasma treatment, then chemical treatment, etc. Like one is this self migration by making lowest free energy state of these functional materials that migrate towards the surface. Suppose the some functional materials are required for a particular application, suppose polymer is formed, then say we can say if we make this lower lowest free energy state, then these will be we can say oriented on the top surface of the polymeric membrane. So, this is we can say this one due to this self migration. There is one another method is called self assembly, like say surfactant molecules coated on the surface by hydrophobic interaction. So, suppose this is the polymeric membrane, and say these are all surfactants, then if these are placed or coated on the top of this polymeric membrane, due to their we can say this one hydrophobic interaction, these will be oriented in the regular fashion, and it has a particular application like this. So, it is we can say this one hydrophobic tail and hydrophilic head is there. So, for that case we can say if it is cationic surfactant, if it is an anionic surfactant, or if it is deuterionic, if it is non-ionic surfactant, depending on the we can say this one surfactant property, we will be able to selectively separate a particular component using that type of self assembly polymeric membrane. The third type is called layer by layer adsorption membrane like this. So, negatively and positively charged macromolecules like this, these are placed like this in the beginning. Suppose on the membrane surface, if the positively charged macromolecules are placed, then and the second layer will be negatively charged like this, these will be placed one by one, and this alternatively will be able to coat these again positively charged macromolecules, and we will be getting these different, and depending on the requirement we will be able to coat what type of charged membrane we require. Based on that we can coat say maybe 1, 2, 3, 4, 5 like this. So, how many layers actually are required, based on that we will be doing this. And say another method of the manufacturing of polymer membrane using graft copolymerization process. This is, you can say, the specific application. For the specific application of the polymeric membrane, that is done like chemical modification method by introducing radicals or on the polymer surface, and then say we can say this one UV, gamma or electron beam or plasma or ozone or hydrogen peroxide, these are used as the grafting. Suppose the polymer is there, we will be using this for a particular application, then we can say we can do this UV or electron beam or some irradiation, and by plasma also we can do, and then maybe selenium also is used. Then on the polymer surface we can say this one radicals are generated, and then using this ozone or hydrogen peroxide. So, we can say this one some radicals are now grafted with different functional groups, and then finally one grafted copolymerized one membrane will be formed, which will be used for a particular application. And another one is the fabrication of the cellulose acetate modified titanium oxide nanoparticles electrospun composite membrane, that is also used for a particular application. Okay, so, for that case, suppose this is the cellulose acetate solution and this is cellulose acetate titanium dioxide solution, and then say the mixed solution was started for 4 hours at 200 rpm speed, and then sonicated for 3 hours in order to ensure the optimum distribution of the TiO2 nanoparticles in the cellulose acetate. And then say we can say this one for the fabrication of different membranes like M1, M2, M3, M4, M5, so many membranes. Suppose different compositions of cellulose acetate, titanium dioxide and acetone DMSC, these are added, and then say these are again electrospun to get a particular say film like this. So, say if the concentration of cellulose acetate is fixed, and then concentration or say dose of the titanium dioxide is changed, as well as this we can say the solvent and co-solvent also is altered, then the we can say property of the membrane also will be varied. Okay, so, based on that, say based on the particular application or depending on a particular application, the membrane will be fabricated. And regarding this manufacture of the cellulose acetate membrane using this phase inversion technique, and then by applying this digital film applicator or casting knife. So, this is the typical procedure actually of the manufacture of phase inverted cellulose acetate membrane. Suppose initially 10.58% cellulose acetate powder was dissolved in acetone DMSC mixture, that is 70:30, and DMF separately with continuous magnetic stirring at room temperature. And then after getting a uniform solution of the cellulose acetate solvent mixture, a fixed amount of each additive, suppose different additives are added, and then stir continuously at least for 1 day. Okay. After that, the casting solution were poured consistently on a glass sheet with the help of one casting knife, keeping an allowance of roughly say 0.2 millimeter or whatever the required thickness of the membrane. So, we need to keep that gap. Then this the knife actually is we can say this one moved from one side of this glass plate to the other side. The resultant film were these one films were exposed to air for about 30 seconds earlier to soaking in the coagulation bath, and for this one bath containing deionized water at room temperature. Then the film actually on the glass plate was this one immersed on a non-solvent like water in this case, and kept for 30 minutes in the coagulation bath. So, there we can see this phase inversion will take place. Up to this it was like this in the liquid phase, meaning inside this solvent. Suppose this we can solvent is suppose DMSC and suppose acetone DMSC DMF, these are there. So, now we are placing this one in water. So, then what will happen, this non-solvent like this water starts to dissolve diffuse actually into the cast film. So, inside this film water will be trying to enter, and at the same time the entrapped acetone, DMSE, DMF will be trying to come out or diffuse from the coagulation bath. So, after the specified time, the exchange of the non-solvent and the solvent has continued until the solution becomes thermodynamically unstable and liquid demixing occurs. Finally, the membrane sheets were this one reserved in deionized water beakers and cut into a circular disc or maybe the whatever the desired shape to put in the filtration cell for membrane experiment, but sometimes that heat treatment also is done. So, this is a typical, we can say this is a composition of this cellulose acetate and we can say polymeric membrane. Suppose the different membranes are there and then cellulose acetate concentration is fixed as 10.5 and sometimes this 12.5 also, and then PEG concentration also is kept, sometimes is 5%, then PVP also is taken like these additives, and then acetone DMSE is taken as sometimes the 89.5%, somewhere it is 84.5%, and then DMF also is taken sometimes at 89.5, sometimes it is 84.5. So, there are so many combinations, but the optimum composition is shown here. Then what is happening inside this coagulation bath, say inside suppose this is the membrane and suppose the we can say the solvent is there inside this one, say solvent will be coming to this water and water will be entering into this membrane. So, due to this exchange of the solvent and co-solvent, so the we can say pores are formed. Okay. So, like coagulation bath is now deionized water, coagulation temperature is maintained at 25 degree Celsius, evaporation time is only 30 seconds and then phase inversion time is 30 minutes. So, in 30 minutes this we can say acetone, DMSE and DMF, these will be coming out and will be mixing with water, whereas this water will be entering into this membrane film. So, that actually takes place in 30 minutes. So, if we allow more than that time also, then after that it will not help anyway, and finally, we will be getting that polymeric film. So, now this one sometimes this in phase inverted cellulose acetate PEG TiO2 membrane also can be formed. So, in that case TiO2 will be added during this we can say this one cellulose acetate dissolution in this acetone and DMSE, and so then we can say this one like acetone DMSE solution is there, then cell in this we can say this one in the cellulose acetate solution we need to put this some polymer additives like this PEG or PVP like this, and then TiO2 nanoparticles also were added and then it is mixed properly, then we can say this one we will be getting casting solution, and then once it is prepared, then we need to put in the glass plate and then using this casting knife or we can say this film applicator we will be getting the film, then it will be placed in the coagulation bath, finally we can get flat sheet membrane. So, depending on the requirement, so we can make this one either circular or maybe we can get the rectangular membrane sheet. And now we can get this one cerium initiated grafted polymerization of polymethyl methacrylate PMMA into cellulose acetate modified with amine functional groups also. In that case we can say this we need to take the cellulose acetate powder, that will be say we need to wash using this methanol and deionized water for 3 times and then was vacuum dried at 60 degree Celsius for 12 hours before this use. Then grafting of this methyl methacrylate into cellulose acetate will take place using 3-necked round bottom reactor vessel with magnetic stirrer inside this aqueous solution. Once this we can say solution is prepared, then 8 gram of the cellulose acetate was added into the reactor vessel comprising 100 ml of an aqueous solution of 0.006 mole per liter of ceric sulphate in 0.4 molar sulfuric acid. The aqueous solution now was stirred continuously at a constant rate of we can say 250 rpm to avoid the influence of the stirring on the degree of this grafting. Then the reaction mixture was purged using this nitrogen gas approximately for 30 minutes prior to the addition of we can say this one in a 25 ml of 0.08 mole per liter MMA monomer. Then the reaction was stopped with the addition of this 5 weight% of this hydroquinone solution at a fixed time of the reaction, and the mixture was discharged into a mixture of water and methanol of 1:1 volume is to volume. Then cellulose acetate grafted PMMA samples were filtered using this methanol deionized, that is also 1:1 volume is to volume mixture for 24 hours and repeatedly washed into using this deionized water. Consequently, the grafted cellulose acetate powders were dried using vacuum dryer at 60 degrees Celsius. Then 6 gram of this cellulose acetate grafted PMMA sample was dispersed in 250 ml DMF water and say 10 volume percent we can say this on TEPA in deionized water, and that was introduced through the ring opening reaction of the methyl group of the copolymer at 70 degrees Celsius for approximately 8 hours. Then the we can say this one resultant product, that is we can say this one CA grafted PMMA TEPA was filtered and washed using methanol and deionized water following drying in the vacuum at 50 degrees Celsius. So, this we can see this that type of polymeric membrane is formed, this one for a particular application. Now, we will be discussing about the preparation of the ceramic membrane. So, the steps are like this: suspension preparation. So, where the starting powders are mixed with the suitable binding liquid. So, we can say this one, that is the suspension preparation. Then we need to do the forming. This includes shaping of the prepared suspension according to the we can say predetermined method. Then heat treatment is required at the end. So, this means using high temperature to bind the membrane particles through a sintering process. Okay. And the common methods are like this. So, there are 4 common methods. One is this paste method, another one dry compaction, the third one is the deep coating method, and the fourth one is the extrusion. So, paste method, that is also widely used, like precursor are mixed together with water or solvent to form paste, and then proper shape is provided followed by heat treatment. When you will be talking about the dry compaction method, their precursors actually are mixed together in dried form. So, there is no need of adding any solvent, and the resulting powder actually is fed into the mold to give it a proper shape. Whatever the shape we need, say depending on that actually we need to make the mold. Like if we want to get a particular say dish shape, then the mold will be of the dish shape. If we want to make a tubular shape, then the we can say the mold also will be the tubular shape. The obtained structures are finally sintered, means this is fired. So, another one is the deep coating. So, ceramic supports are dipped in the polymer solution and then this one calcined or heated. And the fourth one is the extrusion. The ceramic mixtures are mixed with water solvent and fed in an extruder. The resulting structures are then sintered. Okay. And there is one specific we can say this common the specific application of the ceramic membrane using the sawdust based membrane. So, in general for the preparation or for the generation of the membrane pores, the pore forming materials are used like some carbonates. So, here the pore forming material is used as the sawdust. So, there we can say the sawdust is taken, then it is screened through say 44 BSS mesh sieves, and then it is mixed you can say this one, it is using this ball mill actually rotated at 40 RPM. So, the sawdust is mixed with this feldspar, boric acid, sodium metasilicate, kaolin. Okay. Then the mixture actually is pressed into the cylindrical mold by applying this one 100 kg force per centimeter square pressure using this hydraulic press, and then it is dried at room temperature for 24 hours. Then it will be again dried at the 100 degrees Celsius for 12 hours. Then it will be heated at 250 degrees Celsius for 24 hours, and then it will be heated this one from 250 to 850 degrees Celsius with a particular we can say this one heating rate, and then it will be kept at for 5 hours, 6 hours, and then it will be cooled, and then final membrane actually will be formed like your dish shape like this. And the advantages of the membrane separation processes over the conventional processes are huge. So, firstly we can say it is a physical separation process, then no chemicals are used and generally less energy requirement compared to the conventional separation processes, and treatment of the heat sensitive materials like fruit juice etc. will be done, and mild operating conditions like this operable under ambient temperature, then almost no damage to the species under processing and no phase change, and the less capital and running cost, easy to scale up, and we can say this process management is very simple, we can say this with the low manpower. Progress, a membrane process has certain limitations that prevent its widespread applicability. Like this there are two primary factors, that is we can say reversible fouling and irreversible fouling, which result in the decline in the permeate flux. This decline in direct consequence of the change in the membrane permeability. So, with time membrane permeability goes on decreasing and decline in flux actually extremely rapid initially and becomes gradual later on. So, there are we can say this one the consequences of the fouling, like this for reversible fouling we can say this one concentration polarization, and for irreversible fouling we can say this permanent pore blocking. Due to say permanent pore blocking we can say permeability of the membrane is lost permanently, but for reversible fouling due to the concentration gradient we can say polarization, this osmotic pressure increases and viscosity pressure increases as well as the diffusivity value decreases, and partial or complete we can say pore blocking actually starts, and the phase separation also starts, and due to the osmotic pressure we can say driving force decreases, because driving force is delta P minus delta pi. As the delta pi increases, then we can say this one driving force actually decreases and extra resistance is generated, and we can say this one permeability decreases. As a result we can say this one reduction in the permeate flux. So, there are so many this in terms of we can say this one concentration polarization, it is defined as the accumulation of the solute of the upstream surface of the membrane. Like this separation process is going on, and then say permeate actually is collecting. In the beginning permeation rate is very high, but with time as the solutes are deposited on the membrane surface. So, we can say this one permeate flux will go on decreasing. Okay. So, due to we can say this one flow resistance increases, then throughput decreases and fouling increases. Okay. So, this is regarded as the concentration polarization. So, ways to reduce the concentration polarization and fouling. So, it can be noted here that the concentration polarization cannot be avoided completely, but it can be controlled only. So, there are so many these steps like this modification of the membrane surface using plasma treatment or ion beam irradiation, and change in the hydrodynamic conditions in the flow channel, like this increased turbulence, then introduction of the turbulent promoters or wires, then pressure pulsation in the we can say this pumping system, and change in the chemical environment of the solution also, then application of the external body force like DC electric power supply, then magnetic field etc. Okay. So, thank you very much, and in the next class we will be discussing various models and application and some design aspect.